So for our second talk of the session, Adam's going to show us how Haskell would have saved the Mars climate orbiter.
Thanks very much. Can you hear me okay at the back? I'm hoping that I can move around a bit more this way. Great. Exactly. So I'm going to tell you about another Typechecker plugin. It's really useful that Java's just explained to you a little bit about how the type checking process works. And this is using the same feature of GHC 710 that Java and I collaborated on, but taking it in a slightly different direction. So to start off with, let's talk about units of measure. And I imagine most of you have used units in some level. These are things like feet, meters, seconds, or more complex forms like meters per second. And just to sort of get the contrast, the things these measure are called dimensions, so length or time or velocity. I'm going to be focusing on the unit side of this picture. And what you've probably used all of these just in day-to-day life. You measure something in meters, and if you measure something else in feet, then you want to make sure that you're converting appropriately rather than mixing up quantities measured in different units. Because otherwise, well, here's an example of what happens if you measure something that's unitless, something in feet, something in years. And there are more interesting examples too. Garrett helpfully mentioned the Mars Climate Orbiter as an example of a case in which NASA managed to crash the probe into Mars rather than orbiting around Mars, because they'd unfortunately used different units in different stages of the design process and failed to notice this. So it's really quite important to make sure that we're using units consistently. And it seems like somewhere that the Typechecker should be able to help us out. So what we want to try and do is have a system whereby the Typechecker can prevent these kind of unit errors, can stop me from adding something measured in meters to something measured in feet. And moreover, as Java was sort of hinting at earlier, we really want type inference behavior. We don't just want to have to annotate every single time I write a number in my program, or an expression which manipulates numbers. I don't want to have to necessarily annotate all the types. I want some good type inference behavior. And I want to be able to write definitions which are polymorphic in the units they support. It's a Haskell programmer, I hope, doesn't need to be convinced of the value of polymorphism. We want to write definitions which will work for any units, instantiate them at particular choices of units somewhere in our program, and know that we're unit safe. Some things that I won't quite get onto so much in this talk, but I'm also interested in exploring, are being able to automatically infer conversions between different units. We're used to type classes doing some of the work for us. When we're writing a program, we don't just use types to prevent bad programs, but we use them to actually write pieces of program. And inferring conversions is a nice example of that. And I want to do all of this without having to write a language extension in GHC, because I don't know if you've ever tried, but GHC is a very big compiler. It's hard work to extend it with a non-trivial feature. And so I want some slightly more modular story about how we can add features to the Typechecker without having to implement them directly in GHC and be directly tied into the way GHC does constraint solving. So with that, I think I'll switch to a demonstration of what we can do with the system that I'm demonstrating. So let's just start up. This is just normal GHC 710. And I'll import the module. So this is just the library plus some predefined definitions of units so that I don't have to write the definitions now. And I need to tell GHC that I want to plug into the Typechecker. So that's dynamically loading the data.units of measure.plugin module, and now everything I write will have this additional type checking functionality along the same lines that Java was describing for the SMT solver, but in this case there's no SMT solver communication, it's just additions to the constraint solver implemented in pure Haskell. And so what can we do with this system? Well, first of all, I just need to be able to write quantities with their units. So I'm going to use a bit of template Haskell quasi-quotation here. So say I've got some speed, 3 meters per second. I can enter that into the system, and helpfully it will infer that the type is measured in meters per second. So quantity is the type of numbers annotated with their units. And then this base M over base S thing is just a slightly less pretty of writing meters per second. So I can use arithmetic operations on units. So if I've got something measured in meters per second and something measured in seconds, I can multiply them together and get a result measured in meters. And again, the type inference is just figuring out the appropriate unit types at which to instantiate these things. And just to show you that something useful is in fact going on here, if I was to mistakenly try adding my quantity measured in meters per second to my quantity measured in seconds, then I get a beautiful type error. But if I go back up to the beginning of this type error, before GHC helpfully gives me a huge pile of context, it's saying that it could match type base meters per second with type seconds, which I hope you'll agree is not too terrible. I certainly agree that there's more we could do to improve this, but users are being presented with errors which correspond to the type language that they're used to, even if some of the additional context that GHC helpfully supplies in this case is a bit less than helpful. Okay, I'll just stop and ask if anyone's got any quick questions at this point. Square meters. Okay, so I can do something like 5 meters squared. Yes, we just have and there's a bit more to the syntax of units, which I'm not showing now. So yes, you can use derived units. So, for example, I believe I've got newtons predefined here, so I can write newtons and have something measured in kilogram meters per square second. Yes, so if I was to write, for example, a function f(x,y), which, I don't know, is just x times y, plus y times x might be a useful example for later. Then you see that the type of this says if I've got a quantity with value type A in units v, and then another quantity measured in units u, then the unit of the result is u times v.
If you try adding meters and feet, then the type system reason out that these are incompatible with conversion, and therefore different than adding meters and seconds, or meters and feet sort of equally incompatible, like meters and seconds.
So they're at this point they are incompatible. Something I'm not going to have time to show the details of how it works is there is a very clever function convert with an extremely complicated type which allows you to do things like I would like to convert 3 meters into feet, and with a bit of luck it will automatically infer the conversion for me. But the types behind this are rather more unpleasant than I particularly want to demonstrate. I should go on and I'll take some more questions at the end, but I should say a little bit about what it is that's going on here. Okay, so as I've shown in the demonstration, we've got a kind of units, so that's a promoted data type. I'm not really interested in its term level values, but just in its type level values. And then there are some empty type families which are used to construct things in this kind. So we've got one for the dimensionless constant. We've got base units, which are just represented as strings for simplicity. And then we've got multiplication and division of units. And then on top of those, we build this new type quantity, which has some representation type A, which is just the underlying numeric representation, and then a phantom parameter U for the units that are being used. And I've shown you, fortunately, since the demo succeeded, the syntax for building concrete values with their units, and we have some arithmetic operators such as multiplication, whose types capture the requirements for the units to be used consistently. But what's going on here? Why is it the case that if you multiply 4 meters per second by 3 seconds, you get something of the right type? Now, Java helpfully illustrated the constraint solving process that was going on during type checking, and that's exactly what's happening here. So GHC is going to come up with a constraint that says, well, meters per second times seconds had better be equal to meters. And GHC doesn't have any way of solving that. There's no sort of built-in process for dealing with these unit operators. So instead, we need some way of extending the equational theory that the type checker knows about in order to solve these constraints. And in this system, the extension I'm using is unification in the equational theory of free abelian groups. This is very much based on Andrew Kennedy's work in F#, where these kind of units of measure are available, because the free abelian groups have some very nice theoretical properties that make them work very well for using with type inference. In particular, we can get, generally speaking, leaving aside some complicating features, we get more or less principal types. And so the important thing to observe here is that this is a form of non-structural unification. So normally in Haskell, if you had list of A equals list of B, you would know that A had to be equal to B. But for these multiplication operators, that isn't the case. And so that's why they're implemented as type families rather than just being constructors of some unit data type. Because then we would, GHC would helpfully then reason in ways that would be inconsistent with the things the equational theory we're adding supports. Why do we actually want a plugin at all? Why not just encode these things as, for example, Richard's excellent units library does, which is a real inspiration for this work. And it's all about type inference. We want this property that u times v equals v times u, not just for particular concrete choices of u and v, but for variables. And that's crucial to making the nice type inference behavior work. And that's something that you can't achieve if you're encoding the behavior of multiplication using a type family. And that's why we need some special purpose constraint solving behavior and this additional plugins functionality. So I'm not going to talk too much about how exactly Typechecker plugins work, because Java's done a great job of explaining how the constraint solving process works already. The key point is that a plugin allows you to write Haskell code, dynamically load it into the compiler, and extend GHC's constraint solver with some special behavior. So that not only can you write domain-specific language, but you can write a domain-specific constraint solver that allows the type checker to solve the constraints that arise from writing programs in your DSL in a more interesting way. So I'll skip through this in the interest of time. But essentially what's happening, how does the constraint solver work in this case? Well, we're going to look for equality constraints involving the kind unit that I showed you, and then normalize those constraints up to the theory of abelian groups and perform simplification using a free abelian group unification algorithm based on Andrew Kennedy's work. In theory, that's all nice and well and good, and in simple cases, free abelian group unification will just solve the unification variables that have arisen from type checking, and we'll know that the constraint is satisfied, and we're happy. Unfortunately, there are a few slightly more complicated cases in which abelian group unification isn't enough to do all the constraint solving we expect from GHC. In particular, we can have things like universally quantified type variables, where I don't get to pick the value of the unification variable, rather I have to work with whatever value the caller gives me. And similarly, the presence of type families in unit expressions can mean that sometimes we can't solve constraints because the user has written some type family and we don't know anything about it. Or maybe the user has given us some additional information which we would like to take advantage of. So that's where this becomes a little bit more interesting than just taking F-sharp's approach to units of measure and implementing it in Haskell. We've really got some things that can't arise in F-sharp's type system. And so we need a slightly more sophisticated algorithm for solving the constraints, but still taking advantage of the equational unification technology, which means that we get nice properties from our type inference algorithm in the simple case. So to take an example just of what's going on in the constraint solver, suppose we have some given constraints. We know that u times v times u is equal to v, and we know that some function f, some type family f, when applied to 1 gives you 1. So I don't know what f is, just that it's some type family the user's defined. And maybe the type checker is trying to solve the constraint. It's got a wanted constraint, alpha times alpha is equal to f of u. So this is the point at which GHC has given up because it doesn't know how to solve these kind of constraints, and without the plugin it would just give you one of those unsolved constraint errors. But what we want to be able to do is to say, well, because I have a bit more domain-specific knowledge about the abelian group structure underlying these units, maybe I can figure out the value of alpha and discover that actually some of these constraints are solvable. So in this particular instance, well, we're trying to solve alpha times alpha equals f of u, and we don't know what f is, so it's not obvious immediately what the value of alpha should be. But just as Java demonstrated with, we talked about in the context of SMT, sometimes we can derive additional information from a given constraint. And in this case, we can normalize u times v times u equals v. In order to discover that u times u is equal to 1. And then, thanks to the theory of abelian groups, that means that u must be equal to 1. Note that here u is a universally quantified variable. So we're not allowed to choose its value, but we are allowed to derive from the given constraints facts about its value. And so once we worked out that it must be 1, we can substitute that in the wanted constraints and learn that alpha times alpha must be equal to f of 1. But going back to the GHC side, we've got a given constraint which tells us the value of f of 1. So we can make use of that to simplify further and get to the point where the constraint we're trying to solve is alpha times alpha equals 1. But now we're in luck, because not only does that tell us that alpha must be 1, but we're allowed to choose the value of alpha because it's a unification variable. So we can return as a solution to GHC, well, take alpha to be 1 and the constraint solved. So the type checking process can continue. So as I've sort of illustrated in that example, we have the tricky case that we might have unknown type families arising in our constraints. The key idea for how to deal with these is a dynamic unification process, which basically means rather than looking at a unification constraint and saying, can I solve it or do I have to give up right now? Instead, we'll try and solve it if we can, but if we can't, then we'll leave it alone, go on, solve some other constraints, and maybe come back to it later on. Because perhaps the variables involved will become more defined, and that'll help us to solve the constraint. And similarly, we have these given constraints, which I've illustrated can provide extra information. I won't walk through the details of this example because I've not got time, unfortunately. So why should you believe one of these plugins? This was alluded to slightly earlier about the question of whether we can generate proofs. So the system is in place for a plugin to generate a proof of the constraints it solves. These can be expressed in system FC as evidence. And the idea is that they can use whatever axioms they like, and the validity of the proof is based on the consistency of those axioms. And I'm out of time, so I'll conclude with just a quick advert for the other things you'll find in the paper. There's a framework for these Typechecker plugins in general in terms of GHC's outside-in X type checking algorithm. There's a description of the abelian group unification algorithm that I've been referring to, and there's discussion of Rich's excellent units package on which the ideas from this are drawn. So thank you very much, and you can, if you'd like to play around, Cabal install UOM-plugin to try it out, assuming you've got GHC 710, and I'm happy to take questions.
So this looks like cool work. A lot of people have thought a little bit about units in the past. And one of the things about the way that you're doing it is the syntax looks kind of crap, if I'm not overstating it. So do you have a sense as to whether it's possible to have this flexible way of plugging stuff in and yet have a smooth way to, like, I mean, ideally, I know Haskell has complex syntax already. Do you have any sense that you could actually have natural-looking unit syntax that didn't feel like needing heroic effort, and then correspondingly with all the type error messages that come as a result?
Yes, I mean, it's certainly true that we've got, thanks to the quasi-quote, a nice syntax for input, but the syntax for output leaves something to be desired.
But actually, I don't even think that the syntax for input is nice if every time you need to use the explicit quasi-quoting mechanism. Okay. I mean, that's still a problem.
Yeah, that's fair enough. I think there's certainly more to be done there. So I think a really exciting sort of direction that this work can be taken is actually in making it possible to plug into more parts of the compiler than just the constraint solver. And being able to plug into the parser or the pretty printer, I think, would be really valuable for making it possible to sort of make these kind of extensions a bit more modular. But what exactly that would look like, I think, is a difficult question.
So we've gotten to quite a good place with reproducible packaging nowadays with Stack and with Nix. You can even have individual shell scripts that just have a shebang line that runs them reproducibly with the right GHC and the right packages. I worry a little bit with the compiler plugin story. What's the packaging story there? If I have a shell script out on the internet that depends on a type plugin, I notice the Pragma lines don't have versions or package information in them. So what is the packaging story?
The short answer is that there's no complication to the packaging story whatsoever. So this is just a normal Cabal package. It's versioned in exactly the same way as any other package, and you can depend on it in exactly the same way. So when you specify the plugin on the command line, that basically just means load the module in exactly the same way as an import statement.
Oh, wonderful, thanks.
So yes, everything just works the way you'd like it to.
So these axioms that you're using, is it a finite fixed number of axioms set in advance, or do you have to generate them on the fly depending on the current problem you're solving?
So something that I maybe wasn't clear enough earlier is that the plugin I've got at the moment isn't itself generating proofs at the moment. It's effectively it's generating an axiom for every particular instance it needs. In principle, what you should do is the plugin should be able to specify the collection of axioms it needs, which typically will be finite. For example, will be the axioms for the abelian group, but needn't necessarily be so. There's still some work to do to make it a bit more user-friendly for a plugin writer to define the axioms, but that's the basic idea.
Okay, thank you.
So you said the units is a kind, right? It's a promoted data type, so that means that the set of base units is fixed. If I wanted to add my own units to this
here the base units are represented as strings. So that means they're not fixed because I can write any string.
How difficult is it to add a new unit? I mean, you have this quasi-quoter, and there is obviously something in your code that tells you what the name of it is. Is it really trivial, or?
So yes, there's also a quasi-quota or a template Haskell function to add new units, just to make it really trivial. But the key point is that there's a type family called makeUnit with many, many instances, which translates from a string to a unit. So you define an instance of this type family, which typically will just be, so here's an example. So makeUnit of miles is just miles, but for miles per hour, it's miles divided by hours. So that's the idea. It gets a bit nicer if I import some extra modules and remove the redundancy, but...
It fits on a single slide.
Sorry?
So what happens if the programmer tries to raise a quantity to an unknown power?
So yes, one complication with this is that you want the power to be determined at compile time in order to fit into the abelian groups model. There is the ability to express raising to a power which is provided through a singleton type. So there's a bit more flexibility there than sort of not being able to do it at all, but it does complicate matters. Until we have a nice story for dependent types in Haskell, that's, I think, inevitably going to be a bit hard to write. But as the dependent Haskell story improves, so it will be easier to write types like that.
So instead of using the quasi-quota, I was wondering, what about just defining variables called m and s and ft? You could do that initially with a quasi-quota, but once you do that, it seems like I could just write 5 meters per second by writing 5 *m / s, right? That seems like a nice enough syntax. So you don't, right?
Yeah, I mean, I think that's a perfectly good approach, and yeah, that works out quite nicely as well. So the reason for using template Haskell for the construction is not just a syntactic one. We need to make sure that when we define a quantity, that we have a particular unit that we are introducing it at. If I could introduce one of any unit, then I can use that to break unit safety. So there's something to be done at construction, which is why I'm using template Haskell. But you're quite right that we could avoid needing to do it if we predefined the sort of base units as constants.